May I have your attention, please? It's a great honor to introduce the 2018 Lekar Prize Lecture. This is an annual event that was established by a gift from the estate of Mike Lekar. Mike was an astrophysicist at SAO for more than 40 years, having joined SAO at the invitation of Fred Whipple. His work ranged from the use of Vanguard 1 during his time in the Navy to make one of the first measurements of J2 of the Earth, through cosmology, the study of solar system chaos, planet formation, and exoplanets. Mike was particularly proud of having helped establish the WISE Observatory, the first astronomical observatory in Israel. He was also a founding member of Harvard's Origins of Life initiative, which was led by Dimitar Sasolov. As many of you know, Mike was a generative character with many friends and colleagues. He taught many freshman seminars, and if you look through the records of those freshman seminars, you'll see many notable people who went on to notable careers in astronomy. So he drew a lot of people into astronomy. He nurtured lots of careers and many collaborations, and I would say he resolved more disputes than he started, although maybe it was even. But he loved solar system dynamics, and so it's very fitting that we would award the Lekar Prize to Professor Renu Malhotra. We're honored to have her here. Renu, as some of you will know, all of you should know, is a world-renowned dynamicist and is highly recognized, as you'll see from her biography. She's perhaps best known for her work on the outward migration of Neptune driven by planetesimals and how that can explain the entrainment of Pluto and Kuiper belt objects into mean motion resonances with Neptune. And that early work spawned an industry in using this intricate dynamical details about the outer solar system to try to understand the formation of our solar system in extraordinary detail. She's also worked on planetary impacts and cratering, as well as tidal evolution of planetary satellites. Some of you won't know that she wrote one of the earliest papers about the dynamics of planets around pulsars. So she's been working in what we now call exoplanets for a very long time. Renu's work has a signature characteristic, and that is clarity. As theorists are trained to do, but rarely do, she finds the simplest physical model that will explain the phenomena that she's trying to understand, but no simpler. And then she draws remarkable insight from systematically exploring that model. So today she's going to show you some of her results of applying that approach to unseen planets beyond Neptune. So with that, I present you Professor Renu Malhotra.
Thank you, Matt, and thank you, everybody, for coming. It's a real pleasure. It's an honor to be giving the Mike Lekar lecture. I was fortunate to have met Mike on a number of occasions over my career, and my abiding memory of Mike is actually on one occasion he was even talking to me about a job. He was very anxious to understand chaos in the solar system, chaos in planetary dynamics. And he wrote this beautiful review paper some years ago, which just last week I assigned to my class to read as reading material for a survey class on small bodies in the solar system. And I'm really grateful that that review exists. Matt, I think you were a co-author on that paper. So I'm really pleased to be doing this. So let me tell you what I'm going to talk about today. It's been very exciting the last few years. The idea that there might be planets beyond Neptune, of course, is not new. And I'm going to walk you through what's been going on most recently. I'm especially intimidated right now. I have a young member in the audience who just arrived, my niece, who's a sophomore at Harvard, and I hope she will take away something from here. Okay. All right. So let's see. So here's the outline. I'm going to give a very brief history of solar system planet discoveries. I'll review the evidence for the recently hypothesized planets beyond Neptune. And there are two of them. You might have heard. One of them has been in the news a lot, one not so much. This is planet 10, This is the my artist's concept of Planet 10. And this is the one you've heard of before, recently, P9, Planet 9, which is much more distant. So Planet 9 is thought to be about something like Neptune itself, out at about 20 or 30 times the distance of Neptune, whereas Planet 10 is closer in and smaller. It's more like a Mars to Earth-like body, we think, and it's only about 3 times farther away than Neptune. So only, of course, is a heavy word here. Only 3 times farther away than Neptune means it's about 3 times as big as the solar system is in terms of extent. Incidentally, these names are not mine. They're not official names. P9 and P10 are. P9 has been chosen by astronomers. P10 has been chosen by the press. So we'll use these. There's a lot of anxiety about naming planets, and I'm not going to go there. So we'll just call them Planet X. So a very brief history looking for planets in the solar system. So our ancient ancestors all knew about 7 moving bodies in the solar system. And that's why we are stuck with the 7-day week. Okay, had they known of more planets, would we want longer weeks? Okay, these were the classical moving bodies in the solar system. The planets were, of course, Mercury, Venus, Earth, Mars, Jupiter, and Saturn. And these were moving relative to the background stars. The background stars moved, of course, across the sky in their daily motion, but they were fixed relative to each other, whereas the planets moved relative to the background stars. The first planet beyond the classical planets that was discovered was in 1781, and it was a serendipitous discovery. It came about because of new technology. Telescopes got bigger, better, actually got invented and got better, and William and Caroline Herschel are credited with this discovery, and this is a picture of them. So this was due to an advance in technology. It was not expected. What this did to the human imagination was, for the first time, imagine that the solar system was different from the distant stars, and that there were other planets, potentially, beyond the classical planets that were known. So this was a huge, I think, opening of the human imagination about the cosmos. Okay, what is the universe really all about? What is the structure of the universe? Now, once Uranus was discovered and its track was followed, it was realized that it was not following the motion, the Keplerian, following the laws of Kepler's laws of planetary motion, and that there were some deviations. And some mathematicians went to work on this. Leverrier is the famous one, and Adams in England made predictions for how this anomaly might be due to yet another planet beyond Uranus. This was based on mathematics and a little bit of luck. The luck is less well known. The luck is that it turns out the location in the orbital path that Uranus and Neptune had over these decades was relatively almost aligned with the sun. Okay, so that made the gravitational acceleration, the gravitational force from what turned out to be Neptune later on, more visible in tracking the orbital path of Uranus. So also importantly, this was a new test of Newton's theory of gravity, that the new planet, so Leverrier and Adams predicted the mass and position of this unseen planet in the sky, and it was discovered shortly thereafter in 1846. This was a directed search, so we knew where to look for, and it was found. This new planet was found where it was predicted by the mathematicians, and so this was a confirmation, one of the important confirmations of Newton's theory of gravity. What about more planets? So Pluto, there was a long search for what turned out to be Pluto later, the next planet out from Neptune. And of course, this is a famous and well-known story. Every school child in America hears about it. It's a long story. So what it stemmed from was apparent anomalies in the movements of Uranus and Neptune. So once Neptune was discovered, its mass was figured out, it still looked like Uranus and Neptune were not behaving exactly as expected within the known solar system, the known planets now. And it was suspected that these anomalies were again due to yet another unseen planet. And so there was a long search for this unseen planet. Percival Lowell funded this search at Lowell Observatory in Arizona, just up the street from me. Clyde Tombaugh discovered Pluto in 1930. Finally, in 1978, Pluto's moon Charon was discovered, and that nailed the mass of Pluto. So it was long, over those decades, it was suspected that Pluto was not as large as was needed to explain those anomalies. And eventually we knew the mass of Pluto, which turned out to be very low mass, only 1/10,000th the mass of Neptune. For scale, that is about 20% the mass of our moon. Okay, so a very small planet. And so the anomalies eventually were resolved. It was an erroneous mass of Neptune that was giving us those anomalous motions of Uranus and Neptune. So that was resolved. Pluto turned out to be a tiny planet, and it was felt that this was the end of what we know about the planetary system. Of course, astronomers thirst for planets. We look elsewhere, and there are more planets. Are there more planets in the solar system? The challenge for looking for more planets beyond Neptune is that they're faint. These are large distances. We see planets by reflected sunlight. So the farther away a planet is, the fainter it gets. An even bigger challenge is that the farther the planet is, the more slowly it moves in the sky. So we have to wait long times to be able to discern that some object that might look like a star, just a point of light, is actually something that's moving around the sun, that's bound to the sun. So the current approach has been different than looking for anomalies in the motions of planets. What we've been doing recently is looking at distant minor planets, the small bodies, asteroids, like we have the analog of the asteroid belt beyond Neptune called the Kuiper belt, which was discovered about 25 years ago now. The first Kuiper belt object was discovered 25 years ago. And now we have more and more of these. We know about many of these now. So the approach has been to use these minor planets as tracer particles. So their own masses are really small. They respond to larger masses. And so to use these as tracer particles in a statistical way to probe for the gravitational effects of unseen planets. What I mean by that is look for the patterns in the distribution of these small bodies. When you have lots and lots of these small bodies, we can look for patterns in the way they're distributed and how those patterns might be created by the gravity of larger bodies. So hints of this have been around now for the last many years, and there are a number of papers here going back to at least 2002 where people have been speculating that there might be additional massive bodies that are sculpting and shepherding these Kuiper belt objects. Most recently, it's these two groups, Trujillo and Shepard, start in 2014, and I'll talk about their work, and Batagian and Brown 2 years ago, who have really accelerated and greatly motivated the search for additional planets. So today, what I'm going to do is talk about three aspects of what we can think of as anomalies in the minor planets beyond Neptune. The three aspects, the three features of these are, I'm going to tell you about the midplane of the Kuiper belt, what is the average plane around which the Kuiper belt objects are distributed. I'm going to talk about orbital clustering of Kuiper belt objects. Looks like there's some anomalies there. And orbital resonances, potentially, with the unseen planet. This is when the orbital periods might be in a harmonic ratio with a potentially unseen planet, and those produce extra enhanced gravitational effects that we can be more sensitive to. So let me give you a quick overview of the Kuiper belt. This is the outer solar system. All the minor planets, each dot here is a minor planet in the outer solar system. This is Jupiter's orbit. This is Neptune's orbit. The red dots and the white dots are what we call Kuiper belt objects. So they exist approximately outward of Neptune's orbit. So this is what the Kuiper belt looks like top down. Of course, it's not to scale. Each dot here is vastly bigger than the actual physical size of each of these objects. So for scale here is 100 astronomical units. That's 100 times the Earth's distance from the sun. So we're looking at the solar system, which is about 100 times as large as the Earth's orbit around the sun. Now, I should have pointed out, so these might look naively as almost uniformly distributed all the way around the sun. But those of you with keen eyesight will see that there's some non-uniformities already, even in just their the spatial distribution of these red and white dots. The white dots in particular you see are just clustered in two places, this place here and here. These white dots are what the Minor Planet Center calls the Plutinos. For some reason, the Minor Planet Center likes to make them in white and not in red. And these are a cluster of objects that share the orbit of Pluto, actually. And I think it might be a historical artifact that Brian Marsden, who was the director of the Minor Planet Center for a long time, was really enamored of the Plutinos. These are objects which are in an orbital resonance with Neptune. They orbit around the sun exactly in a time period 1.5 times Neptune's orbital period, and they tend to cluster at these places. Those of you with even keener eyesight will notice that the red dots also have some patterns. Here, for example, there's less density closer to Neptune's orbit than farther out, and kind of near Neptune as well. There are other gaps and so on. These different patterns become much more clearer when we look in orbital parameter space. Okay, so orbital parameter space, namely, an orbit is elliptical. It has a long axis called the major axis, and here, this parameter here is the semi-major axis, so so this is the size of the orbit, the mean size of the orbit. Think of this as the mean distance from the sun. But orbits are elliptical, so how elongated they are is measured by the eccentricity. So zero eccentricity is a circular orbit, and these are, as you go up on this axis, we have more and more elliptical orbits. So when we look in this parameter space, this orbital parameter space, we see some patterns that emerge very clearly. We see this clump here. This is those Plutinos, or the objects that are in orbital resonance, the 3 to 2, with an orbital period which is 1.5 times Neptune's orbital period, show up here. But first, let me tell you what all the Kuiper belt astronomers have identified these clusters or these classes of Kuiper belt objects. This is what we call the classical Kuiper belt. It's a somewhat unimaginative name, but it refers to the idea that the theoretical expectation that beyond Neptune, any minor planet belts should be small bodies that are orbiting in approximately circular orbits, approximately in the plane of the planets. And so this is low eccentricity orbits, and we find them in a little relatively narrow belt here between 40 and 50 astronomical units. Okay, so that's 40 to 50 times farther away than Earth is. Then we have these clumps in these orbital resonances with Neptune. There's a whole series of them, a whole sequence of these orbital resonant clusters. And I should have pointed out a couple things here before I started showing these clusters. There are two arcs that I've drawn this way. These are the combination of semi-major axis, the combination of mean radius, mean orbital radius, and eccentricity, where the orbit has a perihelion distance. So you have this elongated orbit. It comes close to the sun, as close as 30 astronomical units. That's where Neptune is. So orbits over here would approach at perihelion the orbit of Neptune. Orbits with a perihelion distance of 26 would get in even closer than Neptune, and these are this turns out to be a kind of boundary for these resonant objects. And the reason for that is that if these Kuiper belt objects come to perihelion at even smaller distances, so up here at higher eccentricities, they would get too close to Uranus over time, and they could no longer stay in resonance with Neptune. And out here is another boundary of perihelion distance, 40 astronomical units, and this is approximately where even Neptune's gravitational reach becomes really weak. So beyond this, Kuiper belt objects that have perihelion distances beyond 40 astronomical units tend to be very weakly coupled to any planetary perturbations, any planetary gravitational perturbations. And then there's this vast population, we think, only a part of which we've seen. It's called the scattered Kuiper belt. These are objects, and they can be very large. This actually goes on to even larger distances from the mean distances from the sun, in orbits that are very, very skinny, very elliptical, and they reach perihelion at distances somewhere not quite Neptune, so beyond Neptune, and between and up to about 40 astronomical units. So they've had some scattering, gravitational slingshot kind of encounters over the history of the solar system, and they occupy this part of parameter space. So in these orbital parameters, we see these patterns appear. There's a particular part of these Kuiper belt objects of which we know only a small number, in addition to these classes that I just showed you, and these are called the detached. Again, not terribly imaginative, but these are called the detached Kuiper belt objects. Now, why are they detached? As I said, this 40 astronomical units for the perihelion distance is about where Neptune's gravitational influence really ceases. And over the age of the solar system, these objects would barely do anything under the known planets. Okay? And yet they exist in these quite elliptical orbits, and they also have quite a large dispersion in their orbital planes. And these have been quite a sore spot for Kuiper belt astronomers. Where do they come from? How did they get there? And there's been a lot of attention paid to these, and we'll talk more about these. Should I talk about this now? Maybe later. Okay. So the first question I'm going to walk you through is this question of what is the midplane of the Kuiper belt. The midplane is quite a sensitive probe of where the big planets are distributed, because the midplane of small bodies is controlled by the gravity of the planets. Now, the planets, as you learned in school, the planets orbit in almost a common plane. All the planets move around the sun almost in a common plane. They are just dispersed a tiny bit. Their orbital planes are dispersed just a tiny bit from each other. But the small bodies are all over the place. Well, not all over, but they're much more dispersed. So they can have big tilts going up to almost 90 degrees in the Kuiper belt. So what do we? This is how we define mathematically what the plane is. We look at the unit vector that's normal, that's perpendicular to the orbit plane, and these are the components of a unit vector normal to an orbit plane. There's the tilt, and then how the tilt angle is rotated. So that's what we call the nodal angle. So two parameters we need to define a plane, an orbital plane. So what we're going to do is ask, actually, since it's two parameters, celestial mechanicians pare this down to something called an inclination vector, which is more or less taking that unit vector and finding how it projects on a reference plane, and we use the Earth's orbit plane as the reference plane. So the ecliptic is what we use as our reference plane. The ecliptic in the year 2000, actually, because the Earth's orbit changes a tiny little bit over time. Okay, so what is our expectation, a theoretical expectation for the midplane of the Kuiper belt? So the Kuiper belt has very little mass, so it does not affect its own plane. So we can think of these as tracer particles, and what we have to do is then look for all the Kuiper belt objects we know of, find out how the planets affect their orbit plane. And this inclination vector that I just showed you, this two-dimensional vector, it turns out that we have for almost 2 centuries, we know something about how small bodies are affected by the big planets in the solar system through this theory called the Laplace-Lagrange secular perturbation theory, which was invented by Laplace and Lagrange actually to study the question of the stability of the solar system. So this is like a linearized theory of gravity for planets orbiting the sun, and you spread the mass of the planets around the elliptical ring and ask how that spread out mass affects the orbital planes and actually other parts of orbital parameters as well. But this is useful for identifying the theoretically expected midplane of any population of small bodies, because each small body reacts to the planets So each small body has its own orbit plane instantaneously, and so here's its inclination vector. But we can decompose that into these two pieces, one of which is enforced by the planets, and the rest of it is what we call a free inclination. So each different minor planet, each different Kuiper belt object will have a different random part, which we call the free inclination, but the forced part is common to every Kuiper belt object for a small dispersion in semi-major axis. So this is a function of what is the mean distance of a minor planet. So where it is, how far it is from the sun, determines this forced midplane. Okay, so for a small dispersion in radial distance, we can calculate what the forced inclination or what the mean plane of a small population would be, a small body population. And these are those two parameters, this inclination, the tilt angle, and the rotation angle of the midplane that's enforced by the known planets. So we go out from Neptune, which is at 30 astronomical units, going out to about 50, approximately twice as far as Neptune, and then go out to about 3 times as far as Neptune. Asymptotically, you'll see that it looks like there's no change, but this midplane is not a flat plane. Okay, there's a warp somewhere in the middle of the Kuiper belt, around 40 astronomical units. There's a great big warp. That has to do with a very interesting phenomenon where the planets, as they precess, as their orbital planes precess over long times, and the time scales here are on the order of million years, the orbit planes precess slowly. The small bodies' orbit planes also precess, and the precession rates vary with the distance from the sun. So at this location, it turns out that Kuiper belt objects will have precession rates, these nodal precession rates that latch on to the nodal precession rate of Neptune. Okay, and so there's this great big, like a swing instability that happens, like you're on a swing and you pump the swing at the natural frequency of the swing. If you pump your legs, you can increase the amplitude. So this produces a warp in the midplane of the Kuiper belt, and we can ask, can we see that in the Kuiper belt objects that we've observed? So there's a small change as you go to large distances, and I should say, what is this plane here? Where does it asymptotically approach? This approaches the plane defined by the total angular momentum of the entire solar system. So if you go far enough away, the entire planetary system behaves like it has a total angular momentum, and this would be the plane that would be normal to the total angular momentum of all the planets. Closer in, it approaches the enforced plane actually approaches the plane of Neptune's orbit. And in here is it's a wrinkle on that plane. So the theoretically expected midplane is something we can calculate like this. It's not exactly flat. And we can look for whether the observed objects, the sample that we have, follows that plane or not. To do that, how big is our sample? Our current sample of the Kuiper belt is only about 2,000 objects. That's not a huge big observational sample, but we can still work with it. We have to go through finding the right sample because many of these, because these are very slowly moving objects, we don't know their orbits super well. So we have to confine ourselves to objects that have been observed long enough that we know their orbits pretty well. There are other complications, for example, those resonant populations that I pointed out. The theory that I just told you about, this Laplace-Lagrange theory that tells us what the midplane should be, what that forced inclination should be, breaks down for resonant objects. So we don't have a theory for that. There's some complications with resonant objects, so we have to get rid of those. And so we come up with a sample that we can actually use to find the midplane, to trace the midplane, the forced midplane in the solar system. And we do this not by so some of you may have been at my talk earlier today where I talked about the midplane of the asteroid belt. There we are spoiled. We have a huge sample. Our sample was something like 100,000 asteroids. And we have a fair sample of the asteroid belt. With the Kuiper belt, we do not have a fair sample. So we have to worry about all kinds of bias issues there. So it turns out there's a better way than taking the average of the unit vectors that are normal to the orbit planes. The better way is to find the plane of symmetry of the sky plane velocity vectors. This turns out, and we can demonstrate that this is a far better way when you have a biased and unfair sample of small bodies, that you can actually home in on the midplane by looking for this plane of symmetry rather than averaging the orbit planes. I won't walk you through the details of that. That's technical things, but please, happy to answer questions about that. So here's our sample then. It's about 930 Kuiper belt objects we can look for. And what we then do is slice them up into these bins in mean distance from the sun and measure their plane of symmetry of their velocity vectors. And these are the results on top of what is predicted. So for most of the Kuiper belt, inward of about 50 astronomical units, you can see that we actually detect this warp, okay, which was really beautiful to see when we did this. That we detect this warp in the Kuiper belt midplane. It's actually quite a substantial warp. The midplane here is about 8 degrees tilted, whereas to the midplane elsewhere. So we can detect this warp, but once we go beyond 50 astronomical units, so this part is consistent with what's expected. But here you see that there's a huge discrepancy between what we expect and what we actually measure. And these samples are not too small for what we need to do to find this plane of symmetry. The samples are actually quite decent sized here. We are running out of objects once we go beyond this distance. There's no more data to work with. So out here in this region where we can measure it, it looks like the plane is not what we expect. It's still, this is a huge big tilt. It's about 7 degrees to the solar system's invariable plane. And we can, one of the harder parts of doing this is to figure out or to estimate the measurement uncertainty. You see these error bars here. Those are kind of tricky to estimate. And I can explain how we got those. So this, we think that between 50 and 100 astronomical units, the midplane is tilted by about 7 degrees, and we know this to better than 97% confidence, actually significantly better. So this is an attempt to visualize. It's very hard to imagine things in 3 dimensions, but we tried to do that. Here's the midplane of the Kuiper belt, that's of the inner solar system where the planets are approximately, and then once you get beyond 50 astronomical units, looks like the midplane is warped, like so. Of course, this is somewhat exaggerated in the tilt, but you get the idea. So we have a warped midplane of the solar system. So how do we account for this, what I would say is an anomaly? So there could be a sample bias still. Can't rule that out. It would have to be a pretty subtle sample bias to escape the method by which we identify the midplane. Could it be that all of this population, that the sample that we have, which is different from interior to 50 astronomical units and outside, most of the sample outside 50 astronomical units is this scattered population, which we think has had these scattering gravitational encounters with Neptune over the history of the solar system. Could it be that that scattering produces a warp? And so you might imagine that might be an answer, because this is a different kind of population, dynamically different history of this population. But then if you think about it a little bit more, you realize that there is no preferred plane other than Neptune's orbital plane or the invariable plane. Okay, so close to the invariable plane. Scattering with Neptune will produce inclination dispersion. As the scattering happens, small bodies can get their orbits tipped from being close to the midplane to being farther away. But different small bodies will get tipped differently, randomly. Okay, so the preferred for the ensemble of scattered objects, the preferred plane will be still close to the invariable plane of the solar system. And so we can get an inclination dispersion, but not a midplane tilt. Can't explain the midplane tilt. 2 other possibilities are that this is some recent impulse perturbation, for example, a star passing close to the sun. Something like that could certainly tilt the entire population of small bodies everywhere in the solar system, in fact. But that kind of tilt would relax. So eventually the star is gone, the small bodies would precess, and the precession timescales there are millions of years. And so that kind of perturbation would get erased on 10 million year timescales. Okay, so either this tilt happened as recently as somewhere less than 10, on the order of 10 million years or less, or it's something else. And the something else is that there's another planet on a tilted orbit that's warping the plane of the Kuiper belt. What kind of planet would it be? So a planet in the same distance range as our sample, okay, which is 50 to 100 astronomical units, can easily change the force, tip the midplane. And how big does it have to be? Something like a Mars mass object with a tilt of about 7 degrees would have a range of about 10 astronomical units where it can tip, where it can tilt the midplane by what we measure. Okay? A larger mass planet would have a bigger range. So something on the order of a Mars to an Earth mass planet in the range of 50 to 100 astronomical units, tilted to the plane of the solar system on the order of 10 degrees, maybe 30 degrees, 10 to 30 degrees, is what can do the job. There's a messy formula that connects the mass of the planet, the distance of the planet, and the tilt of the planet itself to the tilt that we observe. So we have at least 3 quantities that are involved here, and only one constraint because we measure this tilt. Actually, we have four unknown quantities, and we have two measurements of the tilted plane. And so we have this combination of parameters, and not to spend too much time on this, not to belabor this point, basically a Mars to Earth size planet at 60 to 100 astronomical units on some tilted plane is what we need to explain this anomalous tilt of the distant Kuiper belt objects. And this is what my collaboration with a local artist in Tucson produced. The colors here are meaningful. Ask me about them. Okay. So that's what it would look like. Its orbit would be about that big in relation to Neptune's orbit, which is here, and here are the other giant planets. And it would be about to scale as far, but it would be tilted, like so. Okay, so this is interesting. There's a recent paper by Silsby and Tremaine that reported numerical simulations of the early solar system when smaller planets were rampant, planet formation was going on in the outer solar system, and these planetary building blocks, planetary embryos were getting scattered around together with these small bodies. And they report that, remember those detached Kuiper belt objects I mentioned, those things that have Kuiper belt astronomers scratching their heads? They reported that that a Mars to Earth mass, a few, possibly more than one to a few of Mars to Earth mass planetary embryos, if they had been scattered around in the early history of the solar system, in this range of 50 to 300 astronomical units, typically producing tilted orbits, so these planets would end up on tilted orbits, they could account for those detached Kuiper belt objects. A number of people, as I said, have been postulating the possibility of scattered planets in the outer solar system. So it's consistent, I think, this observation that we have, and the estimate that it's a Mars to Earth size object in a tilted orbit producing a tilt is consistent with these theoretical expectations of the history of what went on in the outer solar system during planet formation. This is not all. There are other anomalies that we've been measuring in the solar system, in the outer solar system. There's this group of so-called extreme Kuiper belt objects. So these are those detached objects, part of that detached population, but they're even more detached than the regular ones. So this paper back 4 years ago, Trujillo and Shepard, they reported 2 features that they had noticed in this extreme Kuiper belt population. So what you're looking at here is distance from the sun, mean distance from the sun. Now we are at hundreds of astronomical units. So all our solar system objects, most of the Kuiper belt that we observe is out here in this little corner here. This is perihelion distance going up. So Neptune's distance is about there. And then we are getting to bigger perihelion distances. So these are all the objects we have in our collection so far, all our observational sample. They noticed these 2 properties of these detached extreme Kuiper belt objects, that there was a gap in the perihelion distance. So this is about a dozen objects now. And we see some out with perihelion distances near 80, and many of them near 40 to 50, but a big gap in there. This does not seem reasonable observationally. There ought to be, this there doesn't seem to be any way to explain why there would be this gap. The other thing they noticed was this other parameter, other orbital parameter. So this is again distance, mean distance of the orbit, and or mean size of the orbit. And this is this angle, this angular parameter of orbits. This is only celestial mechanicians love this angle called the argument of perihelion. Physically, what it is here's the orbit of a Kuiper belt object, where it crosses the ecliptic, and if we measure the angle between the perihelion, where this object comes to perihelion, and where it crosses the ecliptic, that's the argument of perihelion. So this peculiar little angle, they noticed, was clustered. Okay, this was clustered around 0. In other words, that argument of perihelion, so these extreme Kuiper belt objects had their perihelion very close to the Earth's orbit plane, okay, which seems very peculiar. Of course, it's not related to the Earth. Neptune's plane is about the same. So this is close to so the perihelion of these objects is close to the plane of the solar system. Bataken and Brown, 2 years ago, noticed something additional. Oh, I should say, Trujillo and Shepard proposed that those two peculiarities could be explained, possibly. They did some numerical simulations, putting in an extra planet on the order of a few Mars mass out to maybe 10 or a few Earth masses, a few Mars mass to a few Earth masses, adding that to the solar system, and they said that in the limited number of computer simulations that they did, that they thought they could find a hint of that kind of clustering of the argument of perihelion. So they proposed that there might be a hidden planet, an unseen planet. 2 years ago, Bataken and Brown revisited this, and they noted something else about this same extreme Kuiper belt objects, that their perihelion directions were clustered like so. So all of these extreme Kuiper belt objects have their perihelia. They come to perihelion in approximately this half circle. Okay, so they're not uniformly distributed all the way around. So these long axes are not pointing everywhere randomly, but rather have a preferential direction. And the other point they made was that even the orbit poles, so the vector that's normal to the orbital plane, that those poles were also clustered in the sky. Okay, and so they made these two observations, and then they went ahead with more computer simulations of putting in an extra planet and asking what parameters of that extra planet would produce this kind of clustering of the orbital angles, these orbital orientations. They came up with this grid of semi-major axis and eccentricity of the planet, and each number in each cell is the probability of success of finding those clusterings in computer simulations with a planet of mass 10 times the Earth's mass. And they homed in on this triangular region of orbital parameter space, where you can see the numbers. The probability of success is on the orders of a few percent. I wasn't particularly impressed with these numbers. I don't know how, well, actually, I know that many astronomers were not especially impressed with these numbers, but they ran with this, and their set of preferred parameters is a 10 Earth mass planet at 700 astronomical units, mean distance from the sun, and in a very elliptical orbit, eccentricity of 0.6, tilted to the plane of the solar system by 30 degrees, and so on. The big challenge, if you're convinced of this planet causing the orbital clustering, is that we don't know where it is in its orbital path. There's no constraint on where in its big orbit. This is an orbit which is more than 10 times farther away from the sun than Neptune is. We don't know where it is. Based on their computer simulations, they could not locate exactly where the planet would be at this time. So the proposed hypothesis is based on these extensive computer simulations. Other people have looked at this. There's a group in France that jumped on looking at, we have exquisite data for one artificial spacecraft, small body in the outer solar system, the Cassini spacecraft, which has been orbiting Saturn for a number of years. We know exactly Cassini's position over something like a decade. And so this group looked at, was there any indication that Cassini's position, or Cassini was experiencing any anomalous gravitational force from an unknown body, from an unseen body. And they looked at the orbit that, the orbital path and mass that Batygin and Brown had estimated, and they found that they could rule out this part of the orbital path, but they couldn't rule out a good part of that the planet could be anywhere else here. Matt Holman and his group looked at that data, looked also at the path that we've been tracking for Pluto over many decades, and they came up. Their conclusion was that that there was really marginal significance for any unknown or unmodeled acceleration on Cassini as well as on Pluto. It does, so the data allows for this planet only at very large distances, nowhere close. So the planet would have to be somewhere close to its aphelion, some hundreds to maybe 1,000 astronomical units away, for it to be, basically it's not visible in the tracks of Pluto, other Kuiper belt objects, as well as in the Cassini tracking, the Cassini spacecraft tracking. Last year, a group in Canada at the University of British Columbia wrote this paper. They've been doing what's considered the biggest, the most extensive survey, observational survey for the Kuiper belt. And they looked at their own data. This survey is responsible for, I think, about half of all the Kuiper belt objects that we know of. And they looked at their data and what kinds of observational biases they had in their own data. They modeled the survey biases, and they produced these bias functions for how sensitive their survey was for different kinds of orbital parameters. And their conclusion was that the strong clustering that we observe of these extreme Kuiper belt objects, these the dozen or so most distant Kuiper belt objects we know of, the biases actually are exactly, would produce this kind of clustering that we see of the orientations that Batygin and Brown were basing their arguments on. Okay, so their conclusion is that the clustering is entirely due to observational bias. Mike Brown disputes that such bias exists in the combined sample of both the Canadian survey and everybody else's observations. So there's that controversy. I don't think that's been resolved. Each group is convinced of their own conclusions. Okay, now this is an updated version of the extreme KBOs. A few more over the last 2 years have been discovered in this parameter regime. And we have now a few that are not in that half circle, that orientation. There are now more that are on the opposite side. So there's a little bit of erosion, I think, of this clustering argument that the orbits of the extreme Kuiper belt objects are clustered. It's still small number statistics. So it could go anywhere. So the point I want to make here, the broader point, is that these new hypotheses about exoplanets, unseen planets, are based largely on statistical arguments, the distribution of small bodies, treating them as tracer particles, lots of computer simulations of a solar system model. And there's plenty of space for pitfalls in that. Notably, I should point out that the Planet 9 hypothesis actually does not account for that perihelion gap I showed you, that Trujillo and Shepard had pointed out in their paper 4 years ago, as well as the argument of perihelion, that little angle. That clustering is not explained by any of these the hypothesis of this Planet 9. Okay, so those two extra features still remain unexplained. My group looked at this problem, of course, when there was a lot of excitement about this 2 years ago, and I should say I looked at this data when Trujillo's paper came out, and I said, this doesn't look very convincing. It makes no sense. Argument of perihelion clustering relative to the solar system plane makes no sense. I dismissed it. Batygin and Brown's work was a little more stimulating. And I looked at this, and I should say I got pretty excited about this. I lost some sleep studying this problem for many nights. The thing I noticed, and this didn't come out of the blue, is that at that time there were only about half a dozen extreme Kuiper belt objects that were recognized back in 2016 by the criterion that we had, which I think is a cleaner criterion. These 6 objects, turns out, had orbital period ratios that are very close to small integers. Okay, so and the reason I looked at this was in Batygin and Brown's work. They argued that this clustering phenomenon by an extra planet would come about because these Kuiper belt objects would be in resonance with that planet, in various orbital resonances with the planet. So I said, well, let's look at these objects. Do they look like they're in any kind of resonance? Well, you don't know where the planet is, so how do you know what resonances to look for? Well, if you reason it through, if each of these is in a resonance with the planet, then their orbital periods in ratio with the planet would be small integer ratios. If you take the ratio of 2 small integer ratios, okay, you get another small integer ratio. So the orbital periods of these small objects should also be in small integer ratios with each other. So I did the simple exercise of taking the ratio of each of these objects with one of them. I picked Sedna, which is a famous dwarf planet in the Kuiper belt. And so if you take that ratio, these are the numbers you come up with. Okay, 1.596. Anybody see that as being close to 1.6? Yeah. Okay. That's 8/5. Okay, and so on. So these, that all of them were pretty close. Was pretty well. It looked intriguing. Okay. Now, of course, you can ask if you take 6 numbers at random, take any 6 numbers at random, would they fall close to small integer ratios? The answer is yes. Okay. They would quite, with some high probability, fall close to small integer ratios. So we did an analysis, a probabilistic analysis. So if you have 6 numbers, all 6 would fall close to small integer ratios. It's a little bit better than random. Okay, so it's marginally significant. Okay, it's not entirely random. So let's run with that. So what kind of orbital period of a planet can you guess to get small integer ratios of orbital periods of these Kuiper belt objects? In the preferred range that Batygin and Brown, they were talking about a 700 astronomical unit semi-major axis. Very close to that, and you can find this very quickly. You don't have to work very hard to do this. You find that at a semi-major axis of 665 astronomical units, all of these 6 objects fall into these close to orbital periods like 3-2, 5-2, 3-1, 4-1, 5-1. Okay? Very close to these small integer ratios now. Of course, the orbital periods are not super accurately measured, so there's error bars in those. These are 3 sigma error bars. And the interesting thing is if you calculate, each resonance is not a single value. Planets can create resonances with some width over the exact, near the exact ratio of 2 integers. Over some small range, a planet can grab on to a small body and keep it in resonance. Okay? So a planet, and how big that width is depends upon the planet's mass. So a planet of mass, so I calculated that a planet of mass bigger than 10 Earth masses would produce enough widths of these resonances that these error bars that we have in the orbital periods of these Kuiper belt objects would be within the widths of the resonances produced by a 10 Earth mass planet. So that's all consistent. And the story got pretty exciting when we saw this. The next step that's really exciting is that if these resonances are real, if there is a planet holding these objects in resonance, we can say something about where the planet is in its orbit, which was something that you couldn't tell from those computer simulations. How can you tell that? This is an example with Pluto's resonance. So here's if you go into a frame that's rotating around the sun with Neptune, so imagine you're sitting on a carousel, going around the sun at an orbital frequency or orbital angular frequency of Neptune's orbital frequency. Pluto makes this nice, beautiful path. Okay, it comes to perihelion again twice before it closes its path, and that perihelion oscillates slowly away from where Neptune is. So if you know where that resonant Kuiper belt object is, you know where the planet that's doing the resonance is not. Okay, so Neptune is not where Pluto comes to perihelion. So we know where these extreme Kuiper belt objects come to perihelion. We can say something about where the planet is not. Okay, so when we do that, and this takes some calculations, we can pick out a path, parts of the orbital path in the sky where the planet cannot be. So this is a planet's orbit, that resonant orbit that we identified, at some inclination. This is the average inclination of those extreme Kuiper belt objects that we speculate might be in resonance. And we can rule out these black parts where the planet cannot be in its path. Unfortunately, about half the orbit path is still allowed, and that means that you have to practically look everywhere in the sky, but there are some places. But if we have more Kuiper belt objects that we can identify in resonances, we can rule out more of this. So maybe it's useful, maybe not. Of course, if you're an observer, you probably won't not look where I tell you. So this is of marginal use. I should say, there's another, when we did these calculations, there's another very interesting, a sweet spot that appears, and that is an inclined orbit for the planet that's inclined about 50 degrees to the plane of the solar system, so inclined a lot, and this is a sweet spot in the following way. This inclined plane actually produces that argument of perihelion clustering. Okay, this allows all these extreme Kuiper belt objects to come to perihelion at a particular place. Okay, this is the only mechanism that I know of. If you have a planet at this inclination, that you can produce an argument of perihelion clustering, and this has to do with some exotic orbits in the three-body problem that actually Henri Poincaré discovered. They're called periodic orbits of the third kind, and they're beautiful, but I don't have time to go into that. Here and then we looked at how such a planet might be located with the next big all sky survey that's coming online very shortly, the LSST, which is going to cover 61% of the entire sky and all of the southern sky and a bit more. And we calculated that this can discover either this planet 10 or planet 9 all the way over the entire parameter space that these planets might exist in, based on what we know of the Kuiper belt. Okay, so that's exciting. That in a few years we'll know for sure. Actually, the LSST would be able to discover these planets in single frames. Okay, that we wouldn't have to do a whole lot of work to except for some very small part of parameter space for planet 9 to identify a new planet in the solar system. So let me summarize quickly. So there are several anomalies in the Kuiper belt which suggest unseen planets beyond Neptune. Each of them is of marginal statistical significance. But these three independent features, because they're independent, I think are sufficiently intriguing to justify continued studies. And on a more, I suppose, a subjective note, I could say that there's a vast amount of space beyond Neptune where the sun's gravity is still dominant. And there's room for many planets out there. So we should, of course, keep looking. Thank you.
Great talk, Renu. Let me ask the first question. So for the mid-plane calculation, you say something like 7 degrees plus or minus 4 is the offset, and that what you really need are more distant Kuiper belt objects. And how many more do you need, and what do you think the prospects are for finding things at those distances?
To reduce the uncertainties in that. So of course, it's a hard job because the error bars reduce only as the square root of n, the number of objects that you find. But finding more objects at those distances is not hard. It's a matter of how much sky you cover at those depths. So LSST, for example, will kill that problem easily. If you increase the number by a factor of 10, you can reduce those error bars by a factor of 3, and really be able to tell very definitively that the midplane is tipped or it's consistent with the solar system.
I have 2 questions. One is, in order for anomalies of this type to be explained by an encounter with a passing star, how close would the star have to come And then the second question is, what about having a much more massive object like a neutron star in a very wide orbit with the sun, something that we wouldn't necessarily see, but that for a very large distance might induce minor perturbations?
So a solar mass star, that's a neutron star, 1.5, so 1.4 solar masses, would have to be tilted. Of course, anything would have to be tilted to make any tilt. So depending upon this, so there's this combination of mass, tilt, and distance. So I showed you some combinations, like an Earth mass out at 100 AU, tilted can do that. So we just need to, you can just extrapolate that same calculation. I think there's a simple extrapolation formula there. For a solar mass, just off the top of my head, I think it would, many thousands of astronomical units with a tilt would do it.
Which would be fine in terms of, say, binary evolution. You'd expect two such stars to generally be pretty far from each other.
Okay, would it have other effects in the solar system?
Or would you have to think about that? Right, but what about the passing star?
The passing star. How close would it have to be? Like I said, the midplane gets erased on a time scale of 10 million years, so we need that constraint. It would have to be within the last few million years. For it, how close would it have to pass? About three times the distances we're talking about would do it. Yeah, but that's still a very small, in astronomical terms, for a star to pass by the sun at 300 astronomical units is astronomical odds.
You mentioned using Cassini as a test particle,
Yes.
but of course Cassini is not the only probe whose position is accurately known. You have the Voyagers, both of them, and New Frontiers. Do any of those contribute to lessening the error ellipse on possibilities?
Matt is the one to answer that question.
So the answer is yes, that other spacecraft could contribute. What you really want is spacecraft that have been in orbit around the sun, for long enough to probe the deviations in the potential. What you'd see, the tidal potential of an additional planet is what you'd like to see, and you could consider spacecraft orbiting Mars, and there are lots of those. And the challenge there is not that there aren't lots of precise data, it's that lots of asteroids also perturb Mars. But it's something to consider. So I would say, things going to head straight out are not as good as things that are kind of orbiting the sun, where you're really getting to probe the potential.
It's actually Voyager does that. Voyager is going
That's true. I mean, it's also challenging when there are unmodeled forces. Right? You really want something that's where you don't have outgassing. You don't want somebody talking about Pioneer anomaly when you're doing the model.
So, how many more Kuiper belt objects are there? I suppose they get to be very small at some point, but.
Well, I think the way to answer that question is to say how many Kuiper belt objects of the typical size we've already observed. Like they're typically 100 kilometer size objects, the ones that we have observed. How many of those are there? I think there are, do you have that off the top of your head? I think they're on the order of 100,000 of those. And we've only seen about 2,000. So there's potential to discover, if we discover, of course they're dispersed, so they'll be at larger distances, smaller distances.
Are they sort of at 18th magnitude or about there?
No, these are typically around 21st magnitude, right?
They range from 21st to 25th.
Well, no wonder you don't see so many.
Yeah, Joey.
Is there a parameter space that LSST could miss, like one of these planet 9, P9 or P10?
Yes, all of the northern sky.
Oh.
Yeah.
All right, that was the point.
But we have northern sky surveys going on too, so it's not entirely. For example, the surveys that do the asteroid surveys. They cover the northern sky. And so actually, just a couple of weeks ago, I've been talking with one of them. You do the pan-stars, but there's the Catalina Sky Survey that covers the northern sky. And they are refurbishing and they're doing deeper surveys. But they also have a very long baseline of imaging. And so we're looking into studying that and looking for distant planets.
So if LSST doesn't find it, it's either in the north or it doesn't exist.
Yes.
Other questions? Yeah.
Awesome. Could I ask about the color?
Okay, so of course this is, when I gave this talk recently to a planetary science audience, and that's all they wanted to know. What does it look like? What kind of geology does it have? So it's actually quite interesting to think about what an Earth mass object that might have formed in the outer solar system might look like, and what its physical properties might be. Could it be geologically active? And the obvious thing to go by is, we saw Pluto. Pluto is geologically apparently somewhat active. So there's low temperature materials on the surface of Pluto, low temperature ices, and there's some source of power that's powering the geology there. So something like a Mars to Earth mass object would have potentially pretty exciting, pretty interesting and novel exotic geology. The colors that were there were meant to, I didn't think about all the intricacies of that when I came up with those colors, but they were meant to actually reflect that icy materials like, especially hydrocarbons that are exposed to 4 billion years of cosmic radiation would produce pretty gooey organics, and orange and teal look like that's what they might represent those. But yeah, so we would expect some pretty cosmic radiation bombarded, low temperature organic materials, hydrocarbons on the surface of a geologically somewhat active body.
So maybe this is naive because I'm not really a planet person, but is it necessary for planet 9 and 10 to have formed in the solar nebula, or could they have been like rogue planets that were ejected from other stars?
Or captured from other planetary systems. Well, for the same, the odds of that happening are actually very low, because two planetary systems would have to come in close enough. So the two stars would have to come something like a few hundred astronomical units, have a passage, or have a close encounter that's about that small. The odds of that generally are pretty small, but if odd things happen, yes, you could exchange planets or small bodies amongst planetary systems. That is not physically not disallowed.
I guess I'm wondering because I think there were some models by Ford and Rossio in the 90s about planets that get ejected from systems. So does that happen often or not?
Well, we don't have observational constraints on that, but theoretically there are lots of computer models that have planets being ejected. There are some observations of free-floating planets now, and so that's not an out of the question idea that there are planets that have been ejected and are floating, not bound to a star. Yes, I think the answer is yes.
So would it explain why they're so tilted from the ecliptic?
If they were captured from another stellar system, yeah. You wouldn't expect necessarily that, each individual one being tilted. But once they're bound to the sun at these distances, their midplane should relax to the solar system midplane. Okay, so that doesn't explain unless it happened pretty recently.
Thank you.
Are there any more questions? Well, Renu, I want to thank you for giving a wonderful lecture.